Hi, in this video, we're going to take a look at generalized estimation equations for generalized linear models. Now, in this situation, I want to do a generalized linear model. For our case studies, we're going to be looking at logistic regression, but I have repeated measurements with some aspects. So maybe I measure the same person multiple times, same location multiple times, same organization multiple times, something like that. So we have what the help documentation calls clustered data. And so a cluster will correspond to like an individual. So maybe we're doing a medical study and we're going to evaluate some aspect multiple times. So let's say that we're going to have 4 observations for every patient. Now, if you think about that for a moment, the observations between the same person should be correlated, right? And we want to take that into a consideration. So regular old generalized linear models does not take this into consideration. This is GLMs make the assumption that different observations are independent of other observations. That just isn't the case for this. So what we're going to do is we're going to invoke some theoretical structure that we're going to like basically tack on to GLMs to be able to account for this. All right, so now there's a couple different ways that we can approach this. We can either have, of course, independent, so we have no correlation between observations. We have exchangeable, so here we have the same covariance between observations, regardless of like when and where they happen for the same cluster level. So in this situation, observation 1 and observation 2 for the same person are just as correlated as observation 1 and observation 4. Okay, and that's exchangeable. Now, autoregressive is where we're looking to see a decay in the correlation over time. So if I had 4 observations for each individual, I would expect to see the correlation between observations 1 and 2 to have a stronger correlation than between 1 and 3, which would have a stronger correlation than 1 and 4. And we would see a geometric decay of the covariance off of that. All right, so the big idea here is I have clustered data, and when I say clustered, we have repeated observations at a certain subject, maybe a location, maybe a person. The examples that for this video are all going to be at the person level. And so this is also more robust than regular old GLMs. And this will come up a lot when we have longitudinal data or repeat measure experiments. And generalized estimation equations, these focus on the mean of the correlated observations within clusters without fully specifying the joint distribution of the observations. Now, the examples I'm going to give, I copied and pasted and modified from the help documentation for GPAC, the R package. So if you're more interested in this, you know exactly where to go. I need to thank the authors for this. All right, so what types of correlation structure can we have? All right, so here I'm looking at within a cluster. So this is assuming that we have independence between different individuals or independence between different locations, however we get to our clusters, but the within cluster correlation, we're going to assume a certain aspect to it. And so independence here is that we're going to have 0 covariance between observations within the same cluster, and we're going to have a constant variance within the cluster. And so here I'm saying the variance of the observations for the individual is constant from each time that we do a measurement on that individual. Now, exchangeable, here we have a constant covariance between observations within the cluster, and we have constant variance within the cluster also. So how do we represent each of these? So the covariance matrix within cluster for independence, you'll notice that I've got a the variance term here, and then I really should put a square on that. I just realized that. And then I have a constant, so we have a constant diagonal matrix or covariance matrix. Now exchangeable, now here you'll notice I have a constant variance in my covariance matrix, and then I have constant covariance. And so, we're expecting the covariance to be less than, the variance. It has to. And so we're taking a number between -1 and 1, multiplying it by the variance to get our covariance. And this is exchangeable where we have that constant covariance across observations within the cluster. Now, autoregressive, we're going to say that we have geometric decay of the covariance within the cluster. How we represent that is you'll notice that, so rho is between -1 and 1, and we can see that it's getting smaller in magnitude because as I go up the diagonal. And so if I square a number that's strictly between -1 and 1, I'm going to get a smaller number than what I had before. I cube it, it'll be smaller than it was originally or when it was squared. And so what's going on is that we have a shrinking of the covariance as time goes on. So if I had a million observations on the same individual, we would expect to see nearly zero for the covariance between the first observation and the millionth observation. Now, unstructured is the wild, wild west. Things can be any way, any shape, any form, where we have the variance can be any darn thing at all. Notice the variance can change from measurement to measurement on the same individual, and each of the covariances can be different. This is what's unstructured. Now, warning about unstructured is that this can take a long time to compute. It can take a lot of memory. This can cause R to crash. This caused R to crash on my machine, by the way. But actually, it didn't crash. It just said, no, not enough memory. No, I'm not doing it. And then we can also do user defined. All right, now something that we can use to evaluate our model is the quasi-information criterion. All right, so just like with BIC, AIC, models with smaller QIC are preferred. And there's some variations off of this. And so to get at the calculations, we're going to use the QIC function in GPAC. QIC is the quasi-likelihood under the independence model information criterion. And here, we're going to use this to choose the correlation structure for our model. So I'm going to have the same data, same formula, different correlation structures, and I'm going to compare the QICs of different models with different correlation structures. Same data, same formula, everything else is the same except the correlation structure. Now, the QICU output, which is the second entry from the function, this is used to compare models that have the same working correlation matrix and the same quasi-likelihood form, but different mean specifications. All right. Now, the quasi-likelihood is the next output from the function. And here we have the corrected information criterion, the CIC. This has been suggested as being a more robust version of QIC when the model mean may not fit the data very well, or when the model with different correlation structures are compared. And then we also have a corrected QIC. And, so this is just a variation that has some advantages over the baseline vanilla version of QIC. All right, now, if I'm using GPAC and to compute QIC, and mass is loaded in my workspace, then we're going to use the GINV function to do matrix inversion. Otherwise, the solve function is going to be used. So if I have just base R, no mass package loaded, I know that solve is going to be used. All right, so let's go ahead and do 3 case studies. And all of these, in my opinion, would be best fit with the exchangeable or possibly the auto-regressive assumption. But you may disagree with me. Whatever way is, you should, whatever, you can look at it, make a different judgment call. All right, so I'm going to be using piping because I always like piping. Here's my options that I want to suppress some of the digits. There's some of the times it's going to be kind of long because of the whole significant digits thing. It's just how these functions work. And I'm avoiding scientific notation, and I'm clearing my workspace. So the first one I'm going to look at is the Ohio Children We Status data set. This is from the GPAC package. All the data sets in this video are from GPAC, by the way. All right, so we have respiratory, as our target variable. We have the ID of the subject. We have their age. And so here, 0 is 9 years old. There's like negative, there's like 1, 0, -1, -2 is how this is coded. And then coding for indication of maternal smoking at the first year of the study. All right, and so here's here's how the data is immediately presented. Now notice I have ID, the same one, 4 times. Now, so this is in long format in relation to in relation to the child. All right, so the patient is in multiple rows. And so here, the level of observations of this data is going to be the measurement, the respiratory output. This is at the level of measurement for this particular data set. Well, if I want to check out the correlation aspect of the target variable with respect to the same person over multiple measurements, this is not the format I need. I need to put this into wide format. I need respiratory and ID to be converted into long format. Now, this was a little bit trickier than I'm used to doing. I had some trouble just getting the tidyr package to do it the way I wanted to. There's probably a better way. This will work. I split the data by the ID variable, and then I spread on age. And yeah. So here I've got each child has their own data frame. Now I'm going to use respiratory and age. So like at this step, this is my data frame. I'm going to take age. I'm going to do -2, -1, 0, 1 are going to become the new column names. And in the corresponding position, I'm going to have the respiratory value. And so now here's what that looks like. And so now I've got the age is coded as a column name, and then I have the result of the respiratory target variable here. Now it's only the head of the data. There are ones in there, but we can't see them because I only showed the top. All right, so what I want to do, I want to look at the correlation of these 4. So this is going to be a measurement of the correlation within cluster, like overall as an average. All right, so here I've got my correlation. Remember, correlation diagonal is always 1. And now here I'm looking at the correlation between -2 and -1 for the age measurement. -1 and 0. Remember, 9 years old is 0, -1 is 8, -2 is 7. And so here we have 0 and 1. And so we can see this. All right, so definitely these correlations are not 0. So we don't want independence. Now, if I was to see as I went up that, so here, if I go soup diagonal, go above one diagonal up and one diagonal up for that. If I saw like a geometric decay of the values, then that would be a sign to use autoregressive. All right, so here I think exchangeable is the best choice, but autoregressive would, like, you could convince me that autoregressive would be the right way to go, because remember, we never really know what's happening when we work with data. I feel like exchangeable is the way to go, but this is an over time aspect, and since we have over time, I would expect to see that just things degrade in their correlation over time. So you could convince me that autoregressive would be the way to go. I'm following what the correlation matrix gives me on this decision, but I'm not like married to it. All right, so something I'm going to do, I'm going to build a baseline model. In that baseline model, I'm going to not even consider the correlation structure. I'm just going to run it, and I'm going to use this just to compare what's going on. Now, when I do this, I'm going through and I'm using the original data set. I'm not using the wide format, and I'm just doing a regular old generalized linear model of logistic regression. Now, when I get to do the generalized estimation equations, I've got the same formula. I have to specify the cluster ID variable, which is ID. Got my data, just like in GLM, family, just like in GLM. Now here, I've got a correlation structure of independence, the help documentation put scale equals fixed. And so this is an additional parameter. The default is false. So when I don't put scale equals fixed, the value of this is false. The scale, since it's not specified in the help documentation, it's a 1, which is a default value when scale fixed equals true. All right, so I do an independence, correlation structure, exchangeable, and then AR1. Now I could have specified unstructured, but then that can take a long time to compute. There can be problems with it, so I just left it alone. All right, so here is the list of all my models. Here's my baseline model to compare on. I'll extract the coefficients in a moment, but we can see that we get some output that's a little bit different off of this. So both of them, I get the formula for the call. It's given to me. I get the coefficients. We get the degrees of freedom, total and residual. Now, in GLM, we get null deviance and residual deviance, AIC. And you'll notice I don't get those. I get the correlation, or I get scale fixed. I get the correlation, number of clusters, and the maximum cluster size. So this is the largest number of repeat observations within a cluster. Now, exchangeable, we get things to be very similar to what I had before. We just see that now, instead of independence, we have exchangeable. And here is the link of the correlation aspect. This is not our logistic regression linkage. We also get an estimated correlation parameter of 0.035. That's very consistent with what we saw in previously. And we get number of clusters and cluster size. Now, when we get to autoregressive, we see that the alpha here corresponds to how much our thing's going to be degrading over time from observation to observation. And so there is a little bit of a difference here. All right, so let's go ahead and take a look at the coefficients. And you'll notice that the default model, baseline GLM, gives me exactly the same coefficients as the independence model. When I get down to the exchangeable and autoregressive, we see a little bit of a difference here. Smoking is, or the interaction is the same as it was up here. Smoking is the same. Age is the same. The intercept is slightly different. Practically negligible, but the autoregressive is very different. All right. And so here, we get, I can do the summary function to get the printout, do my hypothesis testing, do my Waltz test. One thing I do like about this output, that, here is the Z value. Here it actually gives you, it explicitly says walled. So remember that whenever I do a walled test in statistics, if I just have a ton of data, it's going to be statistically significant just because of how, it'll be sensitive to detecting not zero, which is not a high bar. And so here, I like the fact that it explicitly says walled. And, we can go through and do our hypothesis testing as such. Oh, and so another thing that is neat, we can get our estimated correlation parameters and the standard error. That's good, for both of these. We can also get the variance covariance matrix off of that, which, it isn't that interesting. Just showing it to you so that you can see that this is a tool. Now, to compute the QIC, I do not want the GLM model. I want the generalized estimation equation model. So here I am omitting the baseline GLM. All right, we want the smallest QIC we can get. Independence and exchangeable are the same, and autoregressive is slightly bigger. So there isn't a big difference. You could convince me that autoregressive is the right way to go, but when I look at this, I feel like exchangeable is the best choice. which is kind of interesting that we have a correlation, but it doesn't degrade over time. So, Now, when we go through the plots, the GLM gives me the 4 default plots, but when I get to the GPAC models, we just get the residuals. We don't get the full kit and caboodle that we got when we were doing generalized linear models, of course, to help analyze our residuals. All right, so now let's take a look at the obesity from the Muscatine coronary risk factor study. And so this is a longitudinal survey of school-aged children in Iowa. And it had the goal of examining the development and persistence of risk factors for coronary heart disease in children. And so we had in the study, there were height and weight measurement of 5 cohorts of children initially aged in these, and things were measured biennially from 1977 to 1981, and this was on 4,856 boys and girls. All right, and so now we have the identity, the identifier of the children, the gender, the baseline age, the current age at the moment of measurement, the occasion. This is identifying for the recording. So was this first, second, third, fourth, whatever, obese, yes or no, and then a numeric version of obese. All right, so here is the original data. Now, something that's going to come up with this is that I've got age and occasion are going to have like a definite connection with this because we're doing measurements in different years. So the kid got older, and so you can see age 6 was the first measurement, age 8 was the second, age 10 was the third, and we see exactly the same thing on the second subject of data set. All right, so what I'm going to do to take a look at the correlation structure is I'm going to get rid of age, and I'm going to break things out by the occasion. So first observation, second observation, third observation, and I'm going to have the number in terms of obese as the target variable. All right, and so now this is the first child and their gender, their base age, obese, yes or no, and then we can see it just coded this way. All right, and so once again, it's exchangeable or AR1. I would lean towards AR1 just because this is over time. I would expect to see a degradation of the correlation. But let's go ahead and take a look. And I can see I've got perfect correlation between the observations. Now, this is probably a fluke in the data, but if I'm a statistician and I need to model with this, I have to deal with it. So I need to make a choice. Is this exchangeable, autoregressive? I don't know. Clearly not independent. So we'll do whatever works. Now, in the help documentation, they went through and they did a quadratic on age minus the average of their ages. And so I went ahead and did that. They actually replaced age with age minus the average of the age. I left it alone, but you could definitely, you could definitely, convince me to do otherwise. So I did modify the functions from the help documentation. Once again, I'm going to do a GLM every single time, and we're going to have 2 models. We're going to have the reduced model, which only includes gender, and then we're going to do a full model that has gender, age, the quadratic on age, interaction between gender and age, interaction between the quadratic and gender. And you can see that, just go through and try all these different models. I have regular baseline GLM for reduced with independence, reduced with exchangeable, reduced with AR1. Then we have the full models, baseline, full model independence, full model exchangeable, full model AR1, and then we get our output. So just off the correlation, I would not use the GLM, I would not use independence. I know that I want to use exchangeable or autoregressive 1, and I haven't decided yet, am I going to do reduced model or full model? There is a function that, as advertised in the help documentation for the package, that will help you do like a chi-square test. I couldn't get it to run on these models, by the way. All right, so here's just the printouts. We got all the stuff, spit out at us. Here we can compare the coefficients, which is, definitely, where I want to start. We can see that the GLM is exactly the same as independence for the coefficients. And we can see that we're getting a little bit of difference off of the gender predictor variable off of this. Now for the full model, we can go through and compare. We can see that we are getting some difference throughout. Not a huge difference, but there is a difference going on. So we can do our hypothesis testing, go through and dig through this as we wish. There's a lot of models for this, so because it's full and reduced, so good things, good amount of stuff to wade through. Here we can look at the variance, covariance of our coefficients. Now, the one that I want to spend some more time on is trying to decide which particular model should we use. So we know we're going to do exchangeable or AR1, and we're going to do full or reduced. So we have 4 models to consider at this moment. All right, so I have QIC. Let's go ahead and use QIC. So here, for reduced, I can see that AR1 is slightly less, not a whole lot of difference. All right, and if I do the full model, I can see that there's a decrease. It's not an earth-shattering difference, but there is a decrease. And then we see it's even lower for AR1. So here, this is setting me up so that I feel like AR1 is slightly better than exchangeable. Not a big difference. I would go with AR1. It makes sense because things being measured over time. If the measurements were like come up and walk up and measure somebody, and then do something else, measure again, do something else, measure, like things are practically done at the same time, I would be leaning towards exchangeable. Since there is a distinct time gap between observations, I think AR1 is the one I would choose. All right, now for the plots, once again, we get the 4 different plots from the GLM, but when we get to the GPAC models, we just see the fitted values with the residuals. And since I only have 2 levels for for predictor variables, when I have the reduced models, you can see that I only have 2 distinct fitted values going on. Now here, this is from the full model of GLM. And here is the full model independence for generalized estimation equation, full model with exchangeability, full model with autoregressive. So I can dig into this. All right, so now let's do another case study. Now this is going to feel very much the same as what we've done before. We're going to do a clinical trial comparing 2 treatments for a respiratory illness. The data are from a clinical trial of patients with respiratory illness, where 111 patients from 2 different clinics were randomized to receive either a placebo or an active treatment. Patients were examined at baseline and at 4 visits during treatment, and we have the respiratory status of them. Now, something that is going to come up very quickly when I fit this model is that the ID variable, as it's printed in the data, is not sufficient. All right, we have the same ID number for multiple patients on this. I discovered this by just like exploring the model. Since it was coming from the help documentation, I was copying and pasting. I assumed everything was good. No, that was a bad move on my part. You need to go in, do your exploratory data analysis, and make sure Now, I did the first two. I checked to make sure that things were unique, that they look good, at least as far as I could tell off of a data table. Uh, but here I got lazy. And when I got lazy, I discovered, oh, wait, no. ID1, there is an ID1 for each center, male and female. And so that means I've got at least 4 different ID1s. So this is not going to work out. So what I decided to do, I went to concatenate sex, center, and ID. Now, ID variables are a number, they go from like, let's say 1 to 50, something like that. I wanted to have ID variables of constant number of characters because that's just good practice. So how I set this up, I want sex, center. Center is either 1 or 2. It's only 1 digit per center, and ID is either 1 or 2. So I padded the IDs that were just 1 digit with a 0. And that way I have a constant number. And also I have a dictionary order. Like everything is very nice. So if I sort by the ID, I'm going to have males and females. I'll have males at center 1, males at center 2, females at center 1, females at center 2, and then it'll go in order of ID variable. And the order will correspond to the numeric one because of how I padded it. So we have center, which is 1 or 2, like 1 through 50, something like that. Treatment of A or P for treatment or placebo, male or female, age at baseline, then respiratory baseline status, and then ID for each of the 4 visits, and then the outcome. All right, so here's what the data looks like, and you'll notice that this is like all the data for first male at center 1 this is their portion of the data. And so the visit indicates what measurement this was for them. So let's go ahead and spread this out. I'm going to focus on I'm going to take visit. I'm going to make visit the new column header, and outcome is the new value inside it when I convert to wide format. And so now when I do this, you'll notice that now it's sorted by female. So when I look here, I know that this is female for gender, center 1, 25th patient at center 1. And so now I've got everything all nice and clean. Here I've got, so this is female, center 1, 5th ID, female, center 1, 18th ID number, and we can see the result off of this. All right, so now I'm going to go ahead and look at the correlation here. I could have also done baseline. I probably should have considered, kept baseline in here. But oh yeah, so I did have baseline for, or I should have had the 4th one. Is what I meant to say. So it would have been better to have that, but here we are, we're rolling. And so I can see that it kind of degrades over time. And so I'm thinking AR1 would be the best choice. You can probably convince me of exchangeable, but whatever, however it works out. All right, and I'm going to go through exactly the same process I did before. Unfortunately, there are observations where we don't have the actual value in there. And because of that, we're going to have some NAs are introduced by coercion, and there's just nothing we can do about that. On this particular case, we don't have it in the data. I could have filtered it out and filtered out those rows. I just left it as is. And we'll go through and we can see now our coefficients. We can compare them. And once again, the coefficients are pretty close to each other. We do see a difference, different values. And in the summary, we could do our hypothesis testing on individual predictor variables as we wish. Changeable is definitely having some problems on that. I probably have a predictor variable I can get rid of. And a lot of times when you're in that position, checking out the other models that are similar gives you a good indication of what you should remove. Yeah, so probably exchangeable is not the way to go. probably AR1 since I'm not getting any pushback from R. A lot of times, this isn't like, I haven't seen this in a textbook, I haven't seen this in a journal, I haven't seen this anywhere, but typically when you have a model that has trouble fitting and it has trouble producing statistics and doing things for you, a lot of times that model is not the one you want to go with. And so the fact that things didn't work out here for hypothesis testing on exchangeable leads me to believe that I would prefer to go with a different one, which I was already leaning towards AR1 anyway. All right, so let's take a look at the QIC. All right, so we have, see, 47.7, 487.7, 486, 487.9. All right, so this is a little bit bigger, but you know they're pretty tight. I think that AR1 would be the one I would actually go with. And then we get our plots. Definitely missed off of this one. So here, there's definitely a problem here in the prediction. It might be that these subjects are going to have respiratory problems in the future, and it has not been diagnosed yet. Maybe, maybe not. We don't know. All right, for homework, get some cluster data, build some generalized estimation equation models, and post your results on Canvas. And that'll be your homework. Compare the models. Look at the different correlation structures. Well, that's all I've got for you. Life is short. Do math.